So by the way, we've been focusing so far on F is G M1 M2 over R squared. Okay? So we've been focusing on the force between two objects. M1, M2. Now we could do a similar thing that we did in chapter 23. We can say if we get rid of M2, does M1 create a field around it that's independent of the presence of M2? And the answer is yes. Just like a charge creates an electric field around it independent of the presence of another charge. So this object creates an electric field, magnetic field, gravitational field, which we call G, which you've heard of in Physics 1, and we use it all the time. So F equals G M1 M2 over R squared. If we set this equal to M2G, the mass of the M2, we can get rid of M2 and G will equal F over M2. It's going to equal G M1 over R squared, and then R hat is the direction. So notice how akin that is to the electrical force. K, Q1, Q2 over R squared, R hat. Then the electrical field was F E over Q1. So it's just going to be, or we could say Q2, K, Q1 over R squared, R hat. So the electrical field, the units is Newton per Coulomb. So the the gravitational field will be Newton per kilogram. Just like this one was Newton per Coulomb. But Newton per kilogram, because Newton is actually kilogram meter per second squared, right? If you go to Physics 1, Newton is a kilogram meter per second squared. Divide that by a kilogram, what do you get? Meter per second squared, which is the rate of acceleration of an object. That's the units of acceleration. So this is an awesome thing. So you have G actually meaning a couple things here. It's the gravitational field of a planet, and it's also the acceleration that an object feels if it undergoes free fall on that planet or in space, due to that planet. So when I say let's find the gravity inside the planet, I could mean let's find either the gravitational force between two objects inside of a planet, or I could just find the field G, just the G. Okay? So let's do this way. Let's find the G of a planet, and then once we find the G, then we know how to find the force on another planet or on another object by just multiplying the mass of that object. Okay? So let me first show you. Let's call this gravity inside and outside. Okay, so we already know that outside, let's say here is a certain distance away. Because the planet is spherical, it's going to act like a point object. It's going to have a spherical symmetry. So the G is going to equal Gm over R squared, R hat, a distance R away. Let me actually show you something interesting. Let me show you that when we go to the surface, okay, that G will give you 9.8 for the Earth. Okay? So on surface, the G is equal to Gm over the radius of the planet squared, right? So let's say this is let's say we're calculating the G of the Earth. So if we do 6.673 times 10 to the negative 11, the mass of the Earth was, let's go back here, always checking, make sure we got it right. 5.974 times 10 to the 24 divided by the radius of the planet. I didn't give that yet, so this is the first time I'm actually giving you the radius. The radius of the Earth is going to be, it gives us the diameter here, so let's divide that by 2 on the book here. It gives us 12,756 is the diameter of the Earth. So divide that by 2, 6,378 kilometers. 6,378 times 10 to the third, because 6,378 is in kilometers, so we got to multiply that by 10 to the third and then square that. Calculate this, see what you're going to get, and you're going to be amazed that it will equal divided by 10 to the power 6. 9.7998, which is 9.8, right? So 9.7998, I got it. If you round it, you get 9.8. So that's meter per second squared. Okay. By the way, over here, I should actually put negative r hat, because gravity is always attractive. So the gravitational field is always towards a planet, not away. So it's not like electric field, which can be either away or in. It's always towards. So notice that the gravitational attraction is 9.7, which gives you our, this is negative r hat. 9.7998, which gives you your famous 9.8 value. So now, let's find out what would happen if you go inside of the planet. So let's first do a hollow planet, then let's do a uniform density planet, and then non-uniform density, similar to what we did with electric field. So, hollow planet. So imagine some kind of a planet that has almost nothing in there. We could almost say like a hollow spherical shell. It could be even a space station, some kind of future space station where people are living in it. So if you go inside of it, how much would you weigh? Or what would G be, you know? And the answer is 0. Similar to the electric field inside of a hollow spherical conducting sphere, the electric field is 0 because there is no mass inside. Okay, and you would say, since in electrical field terms, you would say, according to Gauss's law, since there's no charge enclosed in the Gaussian surface, the electric field is 0. Well, you could make a similar type of argument here. There's no mass enclosed in that Gaussian gravitational surface, so the gravity there is 0. The other kind of argument you can make, which is basically what's made by Newton, is that if you make a cone, divide up this into different cones, you could say this part of the planet will attract you with a certain force. This part of the planet will attract you with the same force. There's less material here, but it's closer to you. There's more material there, but it's farther away from you. So those two forces cancel. And then this material here, I can make another little cone here. This guy will attract you that way. It will cancel with this guy. So F1, F1, they cancel. F2, F2, they cancel. Okay, opposite and equal. And then this guy here will cancel with this one here. They're farther away. So this one is F3, F3. They all cancel, and you could make an argument that all the cones, all the spherical cones, they cancel, and you basically nothing is left. So it's similar to saying the Gaussian field, the Gaussian surface contains no mass. So G would be 0. And since G is 0, no matter who goes in that planet, no matter what their mass, they will also weigh nothing. So once you go in there, you just sort of float. You know, it's like being in free fall. You know, it's like being weightless. Okay, so now let's do